Thanks, Charles. And thank you all for coming. I'm really excited to be able to speak with you guys. So please feel free to ask me questions. I guess we're supposed to wait until the end, but I'm pretty friendly. I like to chat, so would love to get to know you. I'm going to start out first giving you a little bit of background of who I am. You know, most people, when they see my name, they ask me, so where is this from? Because it looks really odd. And, you know, if you know a little bit about European history, you would likely guess that I'm from a Slavic country, which is actually correct. So my first name is pronounced Tajana. The middle name actually was my maiden name. It's pronounced Šimunić. That is why it has those funny marks on there. And last name, that would be my husband's name, which actually I inherited after I became a US citizen. I didn't actually pick up the name by marriage. So where I come from. As I mentioned, I do come from Europe. On most European maps, Croatia doesn't even have letters Croatia on it because it's so small. The country has about 4 million people. It's right here, this little piece. And what you'll notice is that it's surrounded by lots of other relatively bigger countries than we are, which basically means that we've been invaded many, many different times throughout history, which kind of defines, you know, the way people think about themselves, and you'll see how that becomes relevant in a little bit. What's also interesting is it has a really beautiful coastline and lots of big mountains inside. So to zoom in, here is a better picture. Within Croatia, this is where I grew up. I grew up in the capital, Zagreb. Which is about 1.2 million people, and it's a typical European city. Any bigger European city you go to would look a lot like my hometown. More interesting detail is that I grew up in the rough part of town. So if you look at, you know, big cities, every city has the neighborhood. I lived in that neighborhood, which meant that I went to a lousy elementary school, and that there were a lot of interesting things that happened that probably should not have been happening. The bright thing in this whole story is that my parents were pretty determined that I should do well in school because they viewed this as a way out of the neighborhood. And, you know, as a kid, I really liked math, so it wasn't too hard for me to get excited about math. I was not that into languages, you know, and the fact that I speak English as well as I do today is mostly a tribute to the fact that nobody wanted to speak Croatian to me when I came to America, you know, so I had to learn. So Croatia actually existed as a real-life country in 7th century. It had a king. So for those of you who think that it's brand new, it's actually not new at all. It's been around for many, many centuries. It's just most of these centuries, it was occupied by somebody else. This actually also should let you know that people, Croatian people, including me, are pretty resilient people because the language survived for over 1,000 years. With relatively little changes, in spite of the fact that the official languages were Turkish and German and Hungarian and Italian and all kinds of other languages. Christianization of Croatia ended in 9th century, and what I mean by this is that Croatia officially became a Catholic country at that point. So for those of you who know Christian history, some of the earliest missionaries from, you know, right after Paul's time came through Croatia. So this was fairly, you know, early influence. It was a kingdom in 10th century, and then under Yugoslavia from 1918 to 1991. So I don't know how much you've seen and remember of the war, but in 1991 is when the war started. Yugoslavia covered the territory of Slovenia, Croatia, Bosnia, Serbia, and Montenegro. The war started because basically people who were running the country did not want Croatia to leave. Croatia at that point was earning the most money for everybody. Independence war, as I said, from 91 to 96. And this actually influenced strongly my career, which is why I'm mentioning it now. And you'll see in a second how it influenced it. And then after 96, life has been good. You know, economy has picked up. Things have been largely rebuilt. So you would actually never know that there was a war recently. Looking at this, you probably realize that we've had 3 wars in the last 100 years. And my grandmother lived through those 3 wars. So my grandma was a kid in World War I. She actually fought alongside of my grandfather in World War II. And what's interesting about Croatia, because there was an influence from communism that was fairly strong, a lot of women were involved in fairly important levels in industry right after the war. So many women fought in the war and then after the war worked. And this also defined somewhat who I am today because I watched my grandmothers have careers, and then my mother and her generation also had careers. So it never dawned on me that there was another alternative. I grew up in a society where both parents worked, and it was very, very unusual to have a mom at home. In fact, it was so unusual that when I first saw and met a family in America where the mother was at home, my first question was, what's wrong with you? Why can't you get a job? It just sounds really odd. And then I realized this is just a different way to live, and it's okay. So as I said, Croatia has many different areas, seaside, down on the coast. My grandmother actually lived there, and I spent many summers there. That actually started my love for travel, which got me on a plane eventually to America. Then the mountains and the lakes region, which is in between, in this funny area here. This is where actually some of the toughest people that I know come from, including the grandmother that I told you about. And then the plain area that looks like any other European plains, and that is actually the region I come from. Zagreb is the capital. Area has been settled since prehistorical times, and as I said, it's about 1.2 million people. This is a little bit about how my life went. When I was a kid, I grew up in a family with actually one little sister. That's my mom, my dad. My mom actually is a PhD in chemistry, and my dad also works as a researcher in chemistry. Both of them worked for companies. So as a kid, I remember visiting their labs and thinking, wow, they get to play cool stuff. They have all these toys, and they can make really interesting things. So I set out, I remember being 7, saying, I like math. I like doing research because of what I saw my parents doing, and I told my parents, one of these days, I'm going to get a PhD too, and I'm going to be a researcher. That's what I'm going to do. And I also told them that I did not want to be a chemist. And that turned out to be true. The reason why I didn't want it is because the lab always smelled funny, so that wasn't that attractive. I got into guitar. So in Croatia, of the time as I was growing up, people pretty much all earned about the same salary. You couldn't really excel financially. So it didn't matter if you became an engineer, lawyer, a doctor, or a musician. And at that point, I was actually very good at classical guitar. I was giving concerts and had an option of going to musical academy. So that was one decision, I guess, that I somewhat regret that I didn't continue pursuing this. But I think also I found music and mathematics really relate well with each other. What you see down here is my sister and me playing with a computer. So this computer on the floor is a Spectrum 48, which most of you have no clue what it is. It actually had 48 kilobytes of memory, and it was a computer that took me 2 years to convince my parents to buy for me because they could not figure out why this would be important and why they should spend their hard-earned money, which coincidentally was back then 50 German marks, which today would be equivalent to about $25, $30. So that gives you a little bit of a context of how poor we were in spite of my parents' education. Money was very difficult to come by. We typically had to, be careful what kind of food we bought, and when guests came, there was always a lecture to all the kids. This is what you're allowed to eat. This is what you can't eat. That's for the guests, So it's kind of a weird country in some ways. You can have very highly educated people working good jobs, but not having much money. So that gets me to a quick overview. As I said, 1st through 8th grade, I went to elementary school. This is a picture, actually. The school is still there in my neighborhood. It is a school from a pretty rough neighborhood. So I actually was one of the top students, always in that school. I was very lucky that there was a math teacher who took interest in me and who specifically made me work. So she figured out that I could do the easy math and then gave me separately much harder math problems, which got me excited and made me want to do more. That brought me to the next level. This was high school. So in Croatia, you actually have to take preliminary exam to get into high school. And this was the top high school in the country. So I had the big argument with my parents who said that I should go to language school because languages are important, and I didn't know how to speak them other than my own. And I said, I don't want to do it. I want to do math because by that time, I had been playing with computers, and I discovered I really liked it. I liked the fact that you could type stuff in and it would respond to you, that you could make things happen, by writing a few simple lines of code. I had written a very small game, and I just wanted to learn more. So passed the exam, got into high school, ended up playing lots and lots of video games for first couple of years. In fact, got to the point where I just wanted to finish the last level, and as you guys know, most of these video games, kind of kill you along the way and then restart where you started, which was really annoying. And as a result, I ended up cracking into assembly code. I wanted to, insert the infinite number of lives and finish the game. So I did that. And by that time, I figured I knew everything about computer science, so because, if you can crack into the code, what else is there to know? I've learned since that there's a lot more, but what I was curious about at that point is how does one build this computer? I had a pretty good idea how to write code. As I said, I had a pretty good idea how to break into code. What I had no clue is how does this code actually run? So I opened up my little computer and saw a bunch of chips, didn't know that they were chips, and I thought, okay, this doesn't really tell me anything at all. And that is what got me into wanting to actually learn a bit about computer engineering. So at the 11th grade, I happened to hear about foreign exchange program and told my mom about it, who got very excited, filled out all the applications in English. My English was pretty lousy, as you remember. I got into the program, and a great family in Flagstaff, Arizona, took me in 12th grade. So that was my first interface with American culture. And this was actually the first family where I discovered that moms actually don't always work. And in fact, I remember looking at their application and thinking, this is really odd. And my first phone call when I came to their family to home was, Mom and Dad, these are great people, and she's totally normal. There's nothing wrong with her. She's okay. And it's okay that she doesn't work. And in fact, they turned out to be the closest friends to me and my family. So we're still, in touch with them. They're like grandparents to my kids. So I got into Flagstaff High School, and interestingly enough, I had to graduate from high school, so I had to take all these classes to satisfy requirements. And basically what happened was, for fun, I took AP Electronics. And also for fun, I took AP Calculus. I hadn't had calculus up until then. It turned out that I was actually pretty good at math, in spite of what the math teacher told me as I walked into the class. I was the only one of, I think, 2 girls in the whole AP Calculus class. And the teacher had this attitude that, for some reason, girls weren't supposed to do this. And I thought, okay, let's see what happens. So I aced his class, and that kind of solved that problem. In AP Electronics, what I really liked was building things. So that was the first time in my life that I had a chance to build a computer, and I thought it was really cool. And the computer, in fact, did work at the end, which proved to be quite difficult to get to that point. So this is why when I got to college, I decided to study electrical engineering. So by now, I knew how to buy components. I knew how to put them on the printed circuit boards. I knew how to write simple microcode. What I didn't know is how does one build those components? What's inside of a chip? And I wanted to figure that out. I wanted to build chips for myself. So I knew everything there is to know about a computer. That was the goal. So I studied electrical engineering at NAU, and if you remember, I mentioned that Croatian history will come in handy. Well, so I was at NAU starting from '88 and graduated in '92. In '91, my sister came to visit me in May to learn English, and she was 15 at that time. By the end of the summer, my hometown was attacked, and she actually could not physically go back. Army had surrounded my hometown. I couldn't get hold of my parents. Bombs were dropping. It was really, really bad. So I applied to become her mom and actually became her legal guardian and put her through the same high school that I had just graduated from, which was a little entertaining. I remember showing up at a parent-teacher conference, and the teacher said, "What are you doing here?" And I said, "Well, it's actually my sister." She did really well. So after I finished my bachelor's degree, it was actually bad times in industry, couldn't get a job as a foreign student. I did my master's in Tucson, and then the war was still going on. This was '93. It was actually really, really bad. About 75% of Croatian territory was occupied. Part of my family in Bosnia had been killed by then, and it was clear to me that I needed to quit with a master's and get a job. So I quit and got a great job as a design engineer at Altera Corporation, doing exactly what I had set out to do, designing chips. And it was really cool. It was so much fun to build a brand new device from what we knew customers would want, send it into production, have it come back. And by the way, when these things come back, they almost never work correctly. So you have to debug them, you have to fix them. And then reproduce the next generation. It turned out to be one of the highest selling products that Altera had produced. It's still, in fact, in the market, and people buy it and use it every day. The particular type of chip that I was involved in designing is the type that you can actually reprogram while in the field. So it's not just software, it's hardware that changes its function. And these kinds of devices are used very frequently in large-scale systems like Cisco switches and routers that you need at the heart of the internet. What I also learned about these chips is that power was a big problem. It turned out if you want things to be reconfigurable, you pay the price in that they tend to be bigger than normal chips, and they tend to consume much more energy. So that got me a little bit curious about how does one deal with energy and with power. And it also got me motivated to go a little further. So I applied to Stanford and to Berkeley. At that point in time, I was still taking care of my sister. She was going to college. So I didn't want to move out of Bay Area. Got into both schools, chose Stanford because it was closer to where I was living at that point. Started with my EE PhD, and I went, as I started my PhD, to a talk by Joel Birnbaum, who was running HP Labs at that point. And in his talk, he had this beautiful vision of the future where everybody's going to have mobile devices in their hands. They're going to be walking around, doing all kinds of cool things, watching movies, talking, collecting data from the environment. And I thought, this is so exciting, except how are you going to make batteries last long enough to actually do any of this? So I asked him this question at the end of his talk, and he said, Tajana, give me your resume. So I did, and 2 weeks later, I had a job at HP Labs. So that is how I got started working on what we call embedded systems and embedded devices, and really focusing my efforts on what is actually power management, how do we manage energy in devices, how do we ensure that your cell phone is going to do all the cool things you want it to do for hopefully a whole day instead of just a few hours. So as a part of my HP Labs research, I developed a project in which the focus and the goal of it was to maximize the battery life of one of the first iPacs that HP put out. When we first started designing it, we put an MPEG player, so media player, on there. It played about 10 times slower than it should, and the battery died in about 5 minutes. So it was really bad when we started. It took a lot of work to redesign both hardware and software so you got something more reasonable out of it. So that brings me actually to today. I worked at HP Labs for 6 years, and I also was a research faculty at Stanford concurrently. And what I found is that I really liked working with students, and that is what motivated me to go into computer science in the first place. So I became a professor and really continued to enjoy all of the work that I'm doing, and continue to expand on work in energy efficiency and energy efficient research. And so here is where we get to my current research. As I said, the goal is minimizing energy usage, and part of the big vision actually hasn't changed from when I first started my PhD. The idea is that in the future, we're going to have, and already have, a bunch of sensors in the environment. We're going to have devices, mobile devices that we carry around, which is basically cell phones. And then at the end of the day, all this data is going to make it somehow to the back end, to the servers for processing and to provide feedback to you. If you think about it, energy is a problem at all of these levels. The obvious problem on the outer rims of this picture is the fact that you have batteries. So you need batteries to last long. However, at the data center level, the problem is that you pay a lot of money to actually run these servers. So companies like Google and Microsoft are very concerned with how much money goes to paying for energy versus how much they actually make at the end of the day. And it turns out the algorithms that you need and the code that you need to make mobile devices more efficient is fairly similar to what you need to do for the big data centers. This is why my research group has been able to attract and get involved with a lot of different companies working actually on really a single topic, energy efficiency, but applied to many different areas. So let me start first with wireless systems and with the battery, and then towards the end of my talk, I'll give you a few details on what we do at the data center level. So with the wireless network, I think the best way always to see what the real problems are is to work with people who do real things. So what we did here at UCSD is we developed a large-scale sensor network which spans from UCSD, which is a dot right here, about 100 miles inland. It goes about 70 miles off to the coast, and it's from almost Mexican border up to Riverside County. The dots that you see on this map are only the high-speed antennas. So this is something that runs faster than your cell phone could possibly run, at about 155 megabits per second, maximum speeds of download and upload. These are stationary antennas. They're very big. They sit on mountaintops, and they have direct link to each other. Underneath each one of these antennas are a whole bunch of smaller devices. They're similar to your wireless access points for Wi-Fi. Those devices then talk to literally hundreds of sensors, and I'll show you some examples of applications that we've worked with. So at the 2 layers beneath this top layer, energy is a big problem because these devices run in the field with batteries and oftentimes with solar cells to complement the battery lifetime. So, oops, why is it activating Windows? Don't want to activate Windows. Okay, so here we go. So here's an example of one device. This device was designed by my group. The goal for it is to monitor large-scale structures. So if you have a Coronado Bridge, for example, and something bad happens, an example would be a recent earthquake, you would want to know if this bridge is still okay. And you would want to know it without sending a human being on there to double-check whether there are any cracks. So a device like this could actually do this automatically for you, and it could do it without you having to change batteries very often. This is why we designed it to actually not need batteries at all. So the device uses a solar cell, which you can see here in a prototype, and then it uses supercapacitors. Supercapacitors are sort of like batteries, except they store charge using electricity instead of using chemical approach. As a result, they actually will last a very long time. The negative is that they can't store nearly as much energy as a battery can. So you have to be very careful with how much energy you use and when you use it. This is why we needed to develop algorithms that predict how much sunshine we're going to have. So here you can see days with lots of sunshine and days with not so much sunshine, right, in San Diego. And then based on how much energy there is, we'll run different number of algorithms on the device. So if a day is very sunny, we're going to run lots of detailed tests that can tell you if there is damage, where the damage is on the structure, and what kind of damage it is. To do this, you actually have to run about as fast as your cell phone. And you run an application that's a lot like decoding video. On the other hand, on days where the weather is not as good, what we can do is we can just check whether there is damage. We can't tell you what kind of damage it is, but we can say, there is possibly some damage here. And then, if you have a little patience, we can actually try to figure out what kind it is. And then there is nighttime, where basically we can just tell you, this was the latest result, and here is a few possible locations where there may be problems. We don't know for sure that there is damage, but there might be a problem. The benefit of this approach is that once you put these devices on a bridge, you can leave them for 30 years without touching them. And that is a big deal. Because if you think about having to climb on Coronado Bridge on every single junction that bridge has, that's a big, huge pain. Lots of money and very dangerous for people. So this project was actually very successful. It's been funded by Los Alamos National Lab, and we have deployed it in the field last summer. And this summer, we're actually planning a bigger deployment of about 100 units on a bridge in New Mexico. And in fact, when I finish my talk, a few hours later, I'll get on a plane to New Mexico to actually set up some of these field experiments. We're planning on producing this in thousands going forward, jointly with, hopefully, the state of New Mexico initially, and then later with the other states. Going back to my wireless network, the other thing that we have on this network is devices that help us predict earthquakes. These devices actually have 3 sensors on every single location. Each sensor will monitor shaking of the ground in one of the 3 axes, right? You got the X, Y, Z axis. It'll take this data, and then it'll send it through the wireless connectivity to UCSD for analysis, because the algorithms needed to predict earthquakes are fairly sophisticated. They actually cannot run very well on small devices. This is why they need pretty big solar cells to provide enough energy, and they need huge battery, which you don't see, which is buried underground together with the sensor. The battery is actually a car-sized battery. This project was run jointly with Scripps Institute for Oceanography, and it was so successful that they got funding to put these devices in 1-mile increments throughout western continental USA over these next few years. One of the biggest problems is, as you can see, this is very bulky, and this motivated actually research for my group. The question was, what can we do to make the solar cell and the battery smaller so it can be much cheaper and much easier to deploy it? And I'll tell you in a second, what we actually ended up doing. This was a collaboration with US Navy. What's interesting about this aspect of the project is the fact that you have devices that go under the sea. So it's a video camera that goes on this submersible, and then it'll stream video to the coast, to, again, UCSD Supercomputing Center, where a lot of the algorithms will run to try to detect if anything unusual is happening. Now, you can kind of guess what Navy might be looking for when it comes to unusual things. However, there are lots of applications that are non-military that you could also think of where monitoring video would be useful. Again, same problem with energy. You need to be able to send the data in real time. So you need enough energy to do it. And on top of that, you need to ensure the data comes at the right time when you need it. So if something bad is happening, you know about it. On the very big end, we actually have a couple of observatories on this network that produce huge amounts of data. So Palomar Observatory will produce about 150 megabits of data per night continually, obviously at night because that's when you see the night sky. The fact that they now have high-speed connectivity, so there's a picture of the antenna that they have at the observatory that streams this data to UCSD, enable them to discover new planets. If this connectivity didn't exist, what they would have to do is drive over from Palomar Observatory with a bunch of tapes to UCSD every day, then put the tapes into the computer, analyze the data, and then drive back the next day to run some more experiments. This means that you basically lose about 24 hours for detection of anything. And that can be pretty much losing a possibility of discovering something brand new, like a planet. We've also worked with California Fire Department on detecting wildfires and on helping them deploy people as wildfires happen. So this is a picture of the helicopter right before it takes off from Ramona Air Force Base. Here it is in the flight. It's actually sending data to the mountaintop antenna as it's flying. And what it's sending is video shots of what's going on underneath. Similarly, at the perimeter of the fire, we set up these antennas, which are basically Wi-Fi connectivity, but it's directional Wi-Fi. So that way we can get very good signal at very fast speed in the middle of nowhere. And the problem, again, is the fact that all of these antennas require power. So you either have to have a car, you have to have a car battery, or you have to have a solar cell to do this. This work with California Fire Department was so successful that actually they are now starting to deploy similar devices using our network. And a lot of the images you saw of the last few big fires in San Diego came from our network, in fact. So here are some of the pictures of the shots both during the day and during the night. We had a webcam at one point set in the field, and we actually have this video that shows a small smoke of fire at a large distance. Within 15 minutes, this becomes a raging fire and melts the camera, and you can actually see the stream of the video as it happens. So that gives you a little bit of an idea of how useful having this kind of wireless connectivity is and how important having enough energy to actually do it in the field when you really need it is. Here's an example of a problem we come into. As you put stuff in the environment, you are exposed to the environment, and this means also wind. So one of the antennas sits on top of Mount Laguna with wind gusts that can reach up to 100 miles an hour. And of course, whenever the wind blows that strong, then bad things happen, and somebody has to go fix it. So when you deploy stuff out there, you really want it to work well, you want it to be reliable, you want it to be stable, and you want it to have backup power as well. Here are pictures of a student sitting out in Margarita Reserve. What you see here is her laptop that she works with. This is how she does her research. She studies ecology. And she has this big, huge antenna because she uses the antenna to tap into all of the data from the sensors that are spread throughout the canyon. So instead of her having to climb down canyon walls to check on the status of her experiments, all she does is she opens up this antenna, connects it to her laptop, she gets results over the internet. She goes to a web page and clicks on sensor by sensor. This has literally revolutionized research in fields like ecology, biology, you saw California Fire Department and a lot of other areas. Again, all of it is based on ability to deploy devices that can last long enough and that can also communicate the distance. These are some of the really cool shots from both Santa Margarita Reserve using our motion detect camera and then from California Wolf Center where people are studying wolf behavior. And what they want to do is they want to correlate video of wolves, their body movement with the audio. So this is actually wolf howls. And when they get the audio and video, they're also studying what kinds of howls is wolf producing when posturing in different ways. And they run on these data that you see here, speech recognition algorithms, which are pretty much the same speech recognition algorithms that people run to recognize words in our spoken language. Although from what I've been told, it's much more difficult because wolves don't have words, so there's no natural pause between concepts. to run this kind of analysis takes a lot of energy, and it takes good amount of processing. So designing devices in the field that can do this is very not trivial, and this, again, is something that my group has worked on. So to get back to how do we solve some of these very real problems? As you remember, HP-RAN network has 3 layers. The top layer was the big, huge antennas, which are typically connected to the power line because they sit on a mountaintop where there is power. Middle layer is what we call sensor node cluster heads. These are devices that use oftentimes connectivity at the speed of Wi-Fi on one side, and many different smaller types of wireless connectivity to the sensors on the other side. Their job is to gather a lot of the data from sensors, do some pre-processing, and then send it off to the back end for some more processing and analysis. These devices, these 2 layers, are typically battery operated or also possibly solar operated. So that means that energy is really a key issue for them. So in order to help maximize the energy availability here, we discovered there are 2 things that cause the problem. One is communication. So it turns out that if you actually want to send the data or receive the data, that by far consumes most energy in a system as compared to processing. So in order to solve that, we developed new routing and scheduling algorithms that consume about 60% less power with 10% higher throughput. So what this effectively means is that you can get data faster and you spend about half as much energy. So your battery lasts about twice longer. How we did this was very simple. It's very intuitive. So instead of having a device continually listen and see if the data is coming, what we do is we schedule times when it should listen in such a way that devices that have to get data urgently can get it quickly, so they're scheduled more frequently, and devices that maybe we don't care so much about, so for example, readings of temperature, which doesn't change that often, will be scheduled much more rarely. And at the end, during the times when it's scheduled, the device will be communicating. All other times, it's completely off. It does not hear anything. So it requires very careful coordination between the parts of the system because, as you know, the needs in the system change. So if at nighttime, nothing exciting is happening, Palomar Observatory will be sending 150 megabits per second worth of data, and life will be good. But if at the same time, all of a sudden, a fire happens, we'll need to reroute the data for the fire with higher priority over what the observatory has. So we'll need to change how routing and scheduling happens. So our algorithms needed to be able to detect this very quickly and change very quickly. This has actually been also deployed and has proven to be quite successful in the environment, and has motivated us on a new project, which we call Citizen Sensing, which takes the idea of monitoring environment and combines it with trying to see how this affects our daily health. So as you saw, we have a whole bunch of sensors in the environment already, and we know that the air we breathe, for example, does affect both our long-term health and also, especially for people who have asthma, it will affect their short-term condition. In order to understand the relationship between the 2, we need to understand what you're doing at the particular moment. So are you exercising hard or are you just sitting? And we also need to understand what are the conditions in the environment. And then we wanted to be able to provide feedback to you through your cell phone so you can make better decisions. So we did actually some preliminary patient trials on this project. The focus of these patient trials was on physical activity only. And what we did is we took a group of 63 patients who struggle with obesity. And we gave about half of the patients just a standard form to fill out about how much they were exercising and gave them some tips on how to increase their exercise, which is the typical way that the doctors handle this today. The other half of the people actually got a cell phone and a few sensors that enabled us to figure out what kind of exercise they're doing and give them feedback in real time. So the feedback was very simple. It was through SMS messages, and the messages just said things like, you're doing a great job, you're consumed this many calories, and you've actually exercised enough today, that's wonderful. Or they'll tell you, you may want to consider taking the stairs, you still have X amount, to expand today. Luckily for us, the people who designed the messages did a very good job of wording it, much better than I could. It turned out to be extremely successful. So over 95% of the users said that they would recommend this system to their friends and family. And not only that, but it turned out that the group that actually used our system lost significantly more weight due to increased exercise. And basically what this tells us is if people know what is going on and if they're more aware of how the decisions that they're making change their life, they actually do tend to make the change much more readily than if it's a much more passive and sort of a longer situation. One of the big problems cited was that battery lifetime was too short. And this was because in order to detect activity, we had to use accelerometers and GPS. GPS kills your cell phone battery. It's that simple. So going forward, we wanted to actually optimize energy, accuracy, so how well we can detect what's going on, and then performance trade-offs in wireless healthcare networks at a large scale. So to do this, we'll be looking at sensors that are on the environment, sensors on the body. How do we optimize what kinds of jobs we're running? So what kinds of algorithms we run here, what is done at the cell phone versus what's sent back to the backend server. How these things are separated will strongly affect how much energy is being consumed and therefore how long the battery is. So here's an example of a set of jobs that you may need to do in a very simple case. So in this case, I have GPS, I have blood pressure sensor, EKG sensor, which gives me heart rate. And then I have accelerometers, which tell me the type of body movement you're doing. And then using this, I would run a bunch of different things. So this is just different pieces of code. And at the end of the day, I would find out what have you done, what kind of activity, was there something abnormal? Did something really bad happen? Did you fall? Did you have an asthma attack? Those would be good examples. And then, we would also have notification logs that would say, this is what's been happening to you. Now, with these tasks, we actually developed optimal algorithms to tell us what is the right way to decide which task will run on a sensor, which job is going to run on a cell phone, and which on the back end. This was done by basically writing a set of equations that look like very simple polynomials and optimizing those equations. So we found out that, in fact, if we do optimal allocation of tasks, we can do 20% better for battery lifetime than if we actually just sent all of the data to a big computer on the back end. So your battery is going to last 20% longer if you do this. And then we said, well, this is great, but it's very static. You can do this at the design time, but things change in daily life. People do different things. Wireless connectivity isn't always there, so you have to readjust. So we developed what we call heuristics, which actually will readjust at runtime. And we found out, as these heuristics check and change, depending on what's going on around us, that we can actually get about 80% longer battery lifetime now, which is a very big deal. So this is now, significantly longer, long enough to where you can actually do this on a daily basis and just recharge at night. And as I mentioned, energy is an issue at all levels. I'll just touch on what we're doing at the data center and then break for questions. So at the data center level, we're looking at how we can manage energy, both from the mobile devices and then how that data then gets analyzed at the back end. With this in mind, we've created a whole new center. It's called MuSyC Center, which stands for Multi-Scale Systems Center. And the goal of this center is to see how we assign tasks, again, similar to my example of the healthcare, across all of these scales, and then optimize how well energy is used there. As a part of this center, we have a number of large companies. It's about $3 million center. And I'm running, actually, a data center effort within that. I have about 10 people on my team from universities such as Stanford, Berkeley, USC, and a couple other people. I have people internationally that I work with. And I have to tell you that one of the most exciting things, of getting to this point in my career has been seeing the work that we do go out into practice and change the way things work both in industry and in academia and, see how a team of people can really make a big difference in the long run. As I said, the goal of our work is this multi-scale, cross-layer, distributed, and hierarchical management. And what I mean by this is we want to have the ability to make decisions at all different points in the system in such a way that we get, overall, the best possible solution, right? And I think I'm going to skip through most of the rest of this. So in the interest of time, I can give a lot more details. So that way you guys have a chance to ask a few questions. So to summarize, you've seen things that we've done in ultra-low power systems. You've seen what we've done with mobile devices, with environmental network and with healthcare network. In large-scale systems, the idea is very much similar. The difference there is that now we have a whole bunch of servers in a room, and we need to optimize which jobs run on which server, how much power that server is consuming, and then how much power is spent to cool the server. So all of these come into the play. And as you can see, energy has been a problem at all different levels. So this is pretty much all I had, and I would love to hear any questions from you. Okay.
Thank you very much for telling about your personal history and very fascinating research. So we have time for maybe only a couple of questions. Okay.
Yeah. Go ahead.
Here.
So we can hear you, I guess.
Okay, on energy efficient computing, earlier we had a speaker called Andrew Chien, and he was talking about his 10 by 10 paradigm for energy efficient computing. So how does that relate to what we're doing right now? Or does it relate at all?
Yes, it does actually. So his idea is that you have different types of applications you want to run, right, in a given data center on a given chip. And for each one of these applications, you can design a processor that does it in the best possible way, in the most energy efficient way. Now, designing a processor for every single application costs a lot of money and takes a lot of time. So his idea is, can we take some subsets of applications and design fewer chips? So say design 10 chips, and then figure out a way to assign the appropriate jobs to those 10 chips. In my work, what we have shown, and I didn't talk about this because we ran out of time, is that if you actually do a smart job of assigning tasks to a particular processor that runs it best, you can save about 50% in terms of energy. So it can make quite a big difference. The bigger question is what happens as you put that chip into a computer system? Because if you look at a typical server, how much processor consume is actually a relatively small fraction today of the overall energy cost. A much bigger fraction is due to memory, so having a whole bunch of memory DIMMs on all the time. And it's also due to all of the supporting infrastructure. So cooling, you have a bunch of fans in the server. So as you think about optimizing, making a chip very energy efficient is only one piece of the story. And this is why we've created a whole big center that will address things from a chip level all the way up to a large system level. And in fact, I work directly with Intel, where Andrew Chien used to work. So I know a lot about what's happening there. Good question, though.
Okay,
There is a question up there.
One more question. Okay.
I think she asked a question. Yeah. Or maybe not. Sorry.
Hear that one?
No, it's okay.
Raise your hand again.
A little confused.
Hi. So you're talking about the phones with the with monitoring the people who are obese, and I was wondering, you said that during runtime, a lot of the energy would be used for computing and the data sending and receiving. I was wondering, and you said that it had to adapt so that battery life would be extended. I was wondering how you actually did that. Aside
That's a
from
good question.
Logarithms and
Yeah, so what we do is we monitor what's going on with wireless connectivity. So for example, if you're really close to a cell tower, you have a very good signal, right? And at that point, you're going to be able to send a lot of data very quickly. If you're very far from a cell phone tower, you're going to have a lousy signal, and your cell phone is going to be working extra hard to boost your signal and to send the same amount of data. So it's going to consume a lot more energy to do it. Instead, as we realize that this is happening, we would instead shift to either keeping the data and not sending at all until signal is better, or we would enable a task that can process data locally instead of even having to send any. So there is clearly a difference in what you pay for communication versus what you pay for processing. And what we found is that processors that go into cell phones have gotten much faster, much quicker relative to the rate at which you can communicate out of a cell phone. So it's actually more beneficial in many different applications to spend energy on processing the data on a cell phone and treating a cell phone as a mini server, effectively, than it is to be sending all of the data to an actual server for processing. Yes. So we actually have algorithms and whole big software infrastructure we developed that sits on the server, on a cell phone, and on the sensor. and it can detect changes across all of these devices. Now, obviously, we have not gotten to the point where we could actually deploy this in a real-life setting yet. We have done it in a lab and shown some really nice results, as you saw. We are planning to run a patient trial that will be about 20 patients early this fall. That's probably going to be done right by Tijuana border because we expect air quality to be, questionable at times during September timeframe there. And we wanted to see how people walking through the border and, essentially sitting and breathing this air affects their health. What can we detect?
Okay, that's all for now. So thank you very much.